Hello everyone, let's discuss 4 problems from today's Division 2 round starting with B. You can read it now or listen to my explanation. In my explanation, we have a grid 2 by n, and n is even, and there are 2 players. The first player wants to put every number from 1 to 2n exactly once in every cell of the grid. Then the second player has to move from this cell to this cell, only going right and down. After he moves, he considers every number he met on the path and takes an alternating sum of those numbers, meaning that the first, the third, the fifth, and so on will be with a plus sign, and the second, the fourth, the sixth, and so on will be with a minus sign. The second player wants to minimize the sum, while the first player wants to maximize it. We are asked what's the most optimal way to arrange those numbers in the grid if we are the first player, and we are only given the number n. Let's start by coloring the cells in black and white. And we'll notice that every number that stands in a black cell will enter the sum with the plus sign, and every number in a white cell will enter the sum with the minus sign. Suppose there is some number a in some black cell and some number b in some white cell. If a is less than b, then we can always swap a and b, and if the path used to contain a, it was increased, and if a path used to contain b, it also increased. So any path either stayed the same or increased its value. So for the first player, it's profitable to swap a and b. Thus, if we see such pair of numbers, we start swapping it, and we do it until there is no longer such pair, meaning that all the numbers from 1 to n are standing in white cells, and the numbers from n plus 1 to n stand in the black cells. Now let's consider where the number 2n stands. Suppose it does not stand in one of those angle cells. Then we can always swap this 2n with whatever stands in this cell, and every path must go through this cell. So the paths that also went through this cell didn't change their score, and all the other paths did increase their score. So it's also always profitable to swap those two numbers. So now 2n stands in one of the angle cells. It doesn't matter in which one, suppose in this one. Now let's consider 2n minus 1. Suppose it does not stand in the opposite cell. Then we can again repeat the same reasoning to prove that it's always not worse to put it there. Thus we already know where the numbers 2n and 2n minus 1 have to stand. So we still have to decide only those numbers from 1 to n and from n plus 1 to 2n minus 2. But we know that all those numbers will enter the sum with the minus sign before them. So their effect will be -1, etc., -n. So let's just pretend that we instead need to put those numbers in the grid, and then the score of a path is just the sum of the numbers that occur in this path. Let's say that the sum of all those numbers is s. It doesn't matter what s is equal to, but this s is fixed if we know the n. If you consider such path and such path, they will both have 2n minus 1 and 2n, but all the other numbers that they will contain will be completely different. So if the sum of numbers here is x, then the sum of numbers here is s minus x. So the minimal score between those two numbers will be at least 2n minus 1 plus 2n plus s over 2 rounded down, because one of those two will already be less or equal than S/2 rounded down. So just by choosing one of those two paths, our opponent can already guarantee himself the answer no worse than that. Now we just need to find the arrangement where the answer will be exactly this. And this inequality will already show that such arrangement will be the most optimal. First of all, let's prove that S is odd. The amount of odd numbers here is n/2, and the amount of odd numbers here is n/2 minus 1. So the overall amount of odd numbers in this sum is n minus 1, which is odd, meaning that the sum is also odd. So let's write it down as 2k plus 1. So this S/2 rounded down is this k. Let's consider such arrangement. 2n is in this angle, 2n minus 1 is in that angle. Then we put 1 here, 2 here, 3 here, 4 here, and so on. Eventually, n minus 1 is here, n is here. And then we put n plus 1 here, n plus 2 here, n plus 3 here, n plus 4 here, and so on, until eventually 2n minus 3 is here, 2n minus 2 is here. Let's just prove that the answer for such arrangement will be exactly this. Let's consider such path. It has some score. This path, on the other hand, will have a score smaller by 1. Because we used to subtract this 1 from the sum. Now we'll subtract this 2 from the sum. But this path will have a score, again, larger by 1, because instead of adding this n plus 1, we'll add this n plus 2. But such path will have a score, again, smaller by 1, because instead of subtracting 3, we'll subtract 4. And so on. Every path that you'll consider will be always smaller by 1, larger by 1, smaller by 1, larger by 1. So if the score in this part of the first path used to be, let's say, p, then the analogous scores of parts of all other paths will be either p minus 1 or p. And the score here will be p minus 1. But we know that the sum of p and p minus 1 is s. So p minus 1 is just k, and p is just k plus 1. So the minimal score of a path with such arrangement will be exactly this plus p minus 1, so it's just k. So it's exactly what we wanted to. So we just need to output such arrangement for a given n. Let's look at the implementation. Well, just read n, I create this grid, and first I put numbers from 1 to n, from right to left, and always putting them in the row i%2. Then I put the numbers from n plus 1 to n minus 2, analogously from right to left, and then I put 2n in the topmost leftmost cell, and 2n minus 1 at the bottommost rightmost cell. And then I output this grid. Now for the problem C, you can read it now, listen to my explanation. In my words, you have an array of n integer numbers called A. In one operation, you can take two neighboring elements of this array and either add one to them or subtract one from them. You want to make this array become non-decreasing. You need to output if it's possible or not. Suppose this is our array. Every dot is a value of the array. Let's instead consider the array of differences between neighboring elements. Let's say that every stroke is the difference between those two elements, right minus left. When you add one to a neighboring pair, you increase this difference by 1, and you decrease this difference by 1. And you don't change the other differences. When you subtract 1 from a given pair, you do the opposite. You add 1 to here, subtract 1 from here. But there's a marginal case. If you take two elements at the end of the array. In this case, you just change this difference by 1 or by -1 without changing any other difference. And in such formulation, your goal becomes to just make every difference non-negative. This will mean that the original array becomes non-decreasing. So let's recap which operations we are allowed to do. First, I'll consider the case of odd n. In this case, the n is equal to 7. So on this example, we can do such operations. We can freely change this difference any way we want. So we can set any value we want to this difference. We can freely change this difference any way we want by taking this pair and adding 1 or -1 to it. And then we can also change such pairs of differences, subtracting a 1 from one of the differences and adding it to the other difference. And we can do the same with such pairs of differences. It's clear that if n is odd, we'll have two groups of differences. I'll make it more clear by drawing the arcs here. So this group of differences is not connected with this group of differences. So what we can do in this case is just add a billion to this difference and a billion to this difference, or like a billion of billions, it doesn't matter, a very, very large number. And then we can distribute this billion of billions among all the other differences. So we will first start subtracting 1 from here, adding it to here, like sending this one through this edge. And then we can send this one through this edge here. And thus we can distribute those ones among all differences until they all become non-negative. And we can of course do the same with this group of differences. So we've proven that if n is odd, we can always output yes. Now let's consider an even n. In this case, we can freely change this difference, and we can freely change this difference. And we have such groups. So you can see there's again no problem with this group. We can make it not negative the same way we did before. But there's a problem with this group of differences. The sum of those differences is fixed, meaning that if the sum is negative, we can't make all of them non-negative. But if the sum is non-negative, as I explained before, we can distribute this sum between those differences to make them all equal to 0 or something more. So in case of even n, we just count the sum of those differences and check if it's less than 0. Let's look at the implementation. So we just read the array. If n is odd, we output yes. If n is even, we count the sum of those differences on even positions. And if it's larger or equal to 0, output yes, otherwise no. Now for the problem G, you can read it now or listen to my explanation. In my explanation, this is an interactive problem. The jury has thought of some permutation of length n. You're given this n. You need to find this permutation to within two possibilities. So you need to output two permutations, one of which has to be the permutation which the jury thought of. You can make two types of queries. First query is plus x. Such query will connect with the direct edge every pair of values which have the sum x. And the second query is question mark ij. As an answer to such query, the jury will tell you the minimal distance in the graph you've built so far between the values on position I and position j. If such path does not exist, the answer will be -1. You can perform no more than 2n queries in total, counting both queries of the first and the second type. Consider all those values. Let's say that n is equal to 7. We want to connect them somehow and then ask some queries about the distances in this graph. Of course, we don't want to add too many edges so that any value is connected to others with many different paths, because this will be chaos. But on the other hand, we would like to connect all the values. So first thing that comes to mind is to output the query plus n plus 1 that will connect all such pairs. And then it's very intuitive to output plus n plus 2 to connect such pairs. Now the graph is just one path. And this is very convenient because let's write out the values that we have in the order of this path. It will be 1, n, 2, n minus 1, 3, n minus 2, and so on. And then there will be n over 2 rounded down plus 1. Let's call the where value of the number where it stands on this path. So for the number 1, the where value will be 1. For the number n, the where value will be 2. For the number 2, it will be 3, and so on. So now when we query ij, what we get is basically the absolute value of the difference of the where values of the value on position I and on position j. So if instead of the original values that the jury thought of, they would write their where values, this would also be a permutation. So let's instead try to guess this permutation. And then by this permutation, we'll restore the original permutation P1 and so on. And once again, in such formulation, the problem becomes much more standard. Because now you can just query for the absolute value of the difference between the two values standing on any two positions. So let's instead just solve this problem. There is a permutation. In one query, we can know the absolute value of the difference of the two values standing on any pair of positions. You can make no more than 2n minus 2 queries, because we have already used up 2 queries. You need to output 2 permutations, one of which will be the permutation that the jury thought of. So it's very natural to query such differences, and let's call them A1, A2, and so on. So we almost know the differences between every neighboring value, but we know them to within their sign. So it's either plus AI or minus AI. So to find the signs of those differences, let's also query such pairs. And let's call the results B1, B2, and so on. So we know that if this difference used to have the same sign as this difference, if you subtract left from the right, then B2 will be equal to the sum of A2 and A3. But if they had different signs, B2 will be something else. So by comparing B2 in this case with A2 plus A3, we can know if the difference that has the absolute value of A2 used to have the same sign as the difference which has the absolute value of A3. So for all neighboring pairs of those distances of neighboring elements, we know if this pair of differences used to have the same sign or the opposite signs. Meaning that if we know the actual sign of this difference, then we know the actual sign of this difference. And then we know the actual sign of this difference, and so on. So let's just consider two possibilities. First, if this difference is A1, and second, if this difference is minus A1. In both cases, we can precisely restore all the other differences. Now if you draw a diagram of this permutation, the first value is somewhere here. If we know the differences between every neighboring pair of elements, then we know how the value changes when you step from the first element to the second element, by which amount it changes. Then we know by which amount it changes when you step to the next element, and so on. So you can build such diagram. And so obviously, the lowest point in this diagram will be 1, and from there you can restore all the other values. And we have done it in exactly 2n-3 queries. And then by this permutation, you can restore the original permutation, p. Let's look at the permutation. I read n, I instantly output two queries, plus n plus 1 plus n plus 2. Then I instantly query for the absolute value of differences of where values of every neighboring pair of elements, and I save the result and call it A. And then I do the same for all pairs of elements that have a distance of 2, and I save the result and call it B. The shift array will be the array of differences. I just assume the first difference to have the positive value, so it will be equal to A0. But every next value will be either AI or minus AI. So for every shift starting from 1 to n-1, I first see if the previous used to be positive. Then I check that if the corresponding B is not equal to the sum of corresponding A's, it means that my sign has to be an opposite of the previous sign. So I invert this sign. And then I say that if the sign is not positive, then I need to make the value negative. Then I go through those shifts, I add them up, thus simulating this diagram, and I remember which was the minimal possible point that I get. Then, using this information, I restore the where values of my permutation. Where 0 is minus the minimal shift, and every following value is equal to the previous value plus the corresponding shift. P stands for the path, so it's all the values from 0 to n-1 in the order of which they are located on this path. Then I output first possible answer is P of where I, and the second possible answer is actually if you just mirror this path. Of course, all the distances will not change, so obviously the second permutation is the same, but if every where value is mirrored. So I output those two permutations, and that's the answer. And the last problem for today is E. You can read it now, listen to my explanation. In my explanation, you are given the number n and m pairs AI BI. You need to make a sequence consisting of numbers from 1 to n as long as possible. But the sequence must follow several rules. First of all, the number 1 must occur exactly once in the sequence. And for every pair AI BI, there must be an occurrence of the number BI between any pair of occurrences of the number AI. You need to determine if the maximal length of such sequence is infinite or arbitrarily large. Otherwise, you need to output the longest such sequence. So let's try it out. The first rule in such form: the frequency of the value 1 must be equal to 1. So what can we say about the frequencies of other numbers from 1 to n? For every pair AB, there must be an occurrence of the value B between every pair of occurrences of values A. So for every pair AB, the frequency of A is limited by the frequency of B. So for example, if B occurs 4 times, A must occur at most 5 times. Of course, such rules are not the complete reformulation of the problem. So it's not enough to just say that this must hold. But let's still consider those rules alone. Suppose I have such limitations. f1 is equal to 1, f4 is less or equal to f1 plus 1, and f3 is less or equal than f4 plus 1, and f3 is also less or equal than f2 plus 1, for example. And f2 is limited by f4. And f4 is also limited by f2. So as you can see, those inequalities can get kind of messy, and it's best to show them using a graph. Let's draw an edge from every A to every B. In this case, we'll get such graph. So with the red, I will show the maximum frequency. In this case, it will be 1. This frequency must be no more than this frequency plus 1. So the maximum frequency in this case is 2. This frequency is no more than this frequency plus 1. So it's at most 3. And so is this. So we can see that if we have in our graph some other value from which there is no path to 1, then its frequency is not directly limited this way. Suppose we even have some component of values which are somehow interconnected, but there's no path from this strongly connected component to 1. In this case, I can obviously output infinite, because I can just put this single element in the beginning of the sequence. And then I can just put all those elements one by one infinitely many times. Like 5, 6, 7, 8, 5, 6, 7, 8, and so on. Whatever the interconnections between them, they will all hold true. Because between every pair of 5, there are all other values. And between every pair of 6, there are all other values, and so on. So now let's consider a case where all the values are reachable from 1 via reverse edges, meaning that every value has a path towards 1. It means that every value can be limited using those inequalities, the way I did it for this graph. But if some value has several paths towards 1, of course we can limit it via the shortest path, because such limitations will be the harshest. So if you limit the frequency of 5 using the frequency of 3, you will get limitation 4. But if you limit it to this edge, you get a limit of 3, meaning that the harshest limitation I could put on the frequency of every value is equal to the shortest distance in this graph from this value to the value 1, plus 1. So let's run a BFS via reverse edges starting from 1. The graph will split in such layers. Let's call this layer 0, layer 1, layer 2, layer 3, and so on. And there can be edges from layer I to layer I-1, as I've shown, but there can be also other edges, like within one layer or to any larger layer. And we know that a value which lays in the layer I can be used in our sequence no more than I plus 1 times. So obviously our natural desire is to use it exactly this many times, and such answer will be, of course, the most optimal. Let's see if it's possible. So let's just call values on this layer A1, A2, and so on, A, K3. Let's call values on this layer B1, B2, etc., B, K2. Let's call values on this layer C1, B2, etc., C, K2, and this will be 1. So in this example, we want to use all values A 4 times, all values B 3 times, and so on. So let's just write out all the values A 4 times. Now, in between every pair of those values, and between such pairs also, there must be some of the values which I call B. So let's just write them all here in between. For the values B, between some occurrences of the same value, there must be an occurrence of some A and also some B and some C. But between the occurrences of every pair of the same value of B, there are already all the values of A between every pair of occurrences of such B. And every value of B too, And the same applies also for pairs of the same A values. I forgot to say, there are all other A values in between every such pair of occurrences. So for the B values, we only need to make sure that between every pair of occurrences of the same value of B, there is some value C. But let's just put all values C in those gaps. Remember that we need to use each value of C 2 times. And now for the values of C, we can repeat the same reasoning that between every pair of the same values of C, there are already all the values of A and all the values of B, like in this case. So we just need to make sure that the value 1 is between all the pairs of the same values of C. So let's just put 1 here. So all in all, our scheme used to be this. Write out all the values of A, then all the values of B, then all the values of C, then 1. Then write out all the values of A, all the values of B, all the values of C. Then write out all the values of A, all the values of B. And then the last time, write out all the values of A. So during the first iteration, we have written all those layers. During the second iteration, we have written all those layers. During the next iteration, we've written just those layers. And during the last iteration, we've written just this one layer. Of course, this is just the example when we have 4 layers, but you can see the general idea from here. So let's look at the implementation. Okay, so I read the pairs and I create those edges already in reverse. So I create an edge from B to A. Then I just do this DFS, and then I see that if there is no path via those reversed edges from the value 1 to some of the other values, then I output infinite. Otherwise, I output finite and find the maximal distance. And for each distance, I create a list of vertices that have such distance. I call it var of di. And then I just do those iterations. J fixes the lower limit, and I always goes from xd to this lower limit. And this lower limit is always higher. And when I fix I just push back to the answer all the values from this layer I. And then I output the resulting sequence. That's it. That's it for today. Thank you for watching. I remind you that I give private lessons on competitive programming. If you are interested, contact me on Telegram. Bye.